So I'm going to start a little before where we left off in the last class and go over a little bit of the trailing portion of the last lecture to cover this business of the blanks. Now, we had mentioned earlier that in the standard procedure, in the basic procedure that we had discussed earlier in the class, there was no way for us to distinguish between repetitions and just one extended symbol, like in this example. So we introduced this blank symbol, where the blank symbol is basically an invisible symbol. It acts like any other symbol, except that if you got an alignment of the kind shown in the first line here, and then you compressed everything, the blank would get compressed, but then it is invisible, you don't actually see it. And so the compression of this first sequence would be read, whereas the compression of the second sequence is going to be read because there's a blank on either side of the first E. The blank is separating out the two E's, but is not visible. And so what this meant was that if we had a word sequence of this kind, a symbol sequence of this kind with B, E, E, F, then when you created an alignment of the symbol sequence to some input and then compress things, you may or may not have an initial blank because the blank is invisible. The burr must happen. Then the burr could or could not be followed by a blank because the blank is invisible. But then there must be an E that follows. So what this graph shows is that you could either have an E following a burr or a blank following a burr, after which there's an E. Now, subsequently, you have an E and an E again. So you cannot skip the blank, because when you skip the blank, if you compressed it, it would just become a single E. So anytime you have a repetition of symbols, you must have a blank in between. So again, this blank is invisible, right? But it makes sure that the repetitions stay distinct. And then again, in this last bit, when you have an E followed by a F, you have the blank in between is optional because, again, it's invisible. So given this, when I compose a graph of this kind for finding all valid alignments of B to the input, then we know that there's an optional blank before the burr. There's an optional blank between the burr and the E. There's a mandatory blank between the two E's. There's an optional blank after the E and the F, and an optional blank afterwards. Again, these are optional because when you compress the alignment, they will disappear. They are invisible symbols. And so if I construct the graph for this one, it's going to look like this. Again, the blank, of course, in the graph, you always have horizontal edges. Then from a blank, you must go to the next symbol. So from all rows corresponding to blanks, you just have the one edge going to the next row. From the burr row, you can either, you of course can continue the burr. These are repetitions, which will get compressed out. From the burr, you can either go to a blank or skip the blank altogether and go to the next E, because the blank is optional between burr and E. And so if you check the burr row at each point, you either have a horizontal edge, an edge one row down, or an edge two rows down. Then if you look at the E row, in the case of the E, you have to go through the blank to get to the next E, because if you skipped it, then the two E's would get compressed to a single E. And so blanks are mandatory between repeated symbols. And so in the E row, you see you have the horizontal edge to account for repetitions. Then you have an edge going to the blank, and edges only from the blank to the next E. So anytime you want to, any path from the beginning to the end over here is always going to go from an E to a blank to an E. And so here's the entire graph. You'll observe that any path from here, from any of the first two symbols in the top left to any of the two symbols on the bottom right, is going to be a valid alignment of B phi to the input where in some paths you'll have a blank at the beginning, and some you'll have a blank at the end. And some paths might have blanks between the B and the E, others might not. But every single path is going to have a blank between the two E's. So did that make sense to all of you? This little construction? If it did, please raise your hand. Yeah. So again, the blank is an invisible symbol. It's a generic thing. And so it's like any other symbol. The only place where it behaves is, differently is when you have repetition. So that's why we introduce it everywhere else. But you will also see that. So one of the reasons for this is when you're actually performing your decoding, then you're going to compute a blank probability everywhere. And so the blank just gets used as an optional entry between symbols. But you'll see something interesting about why the blank is useful in other places as well when we get to performing actual decoding, right? So assuming that we understand where this graph comes from, then note that the first and last columns are also allowed to end at initial and final blanks because these are invisible. Skips are permitted across a blank, but only if the symbols on either side are different. So for blank and blank, the symbols on either side are the same. So there's no skip from the first row to the third row. For B and E, the symbols on either side are different. So there's a skip from B to E. For E and E, the symbols on either side are the same. So there's no skip from E to E. So the rule is very simple. You allow a skip across two rows if the symbols on either side are different. Otherwise, the only allowed transition is to the next row. And now, the forward algorithm is very straightforward. You would actually have the symbol probabilities in these first two entries of the table. The rest of them are zero because these are not permitted as the first node in any path from the beginning to the end. Then for subsequent rows, at each node, you would be adding the alphas of the two parents. So for example, for this guy here, you'd be adding the alpha of this node and the blank immediately above it. And then if this symbol is not the same as the symbol two rows above, then you're also going to be adding the alpha for that row. So here is the rule again. For any row, you're going to be summing the alphas of the two nodes immediately to the left of it. So the one just to the left and the one just above it. And if that symbol is not the same as the symbol two rows above, then you're also going to be adding in that alpha. So the outcome of that is going to be the sum of the alphas of all the parents of any node. And then once you've summed up the parent alphas, you multiply the symbol probability itself, and that's going to give you the alpha for each node. So here, for example, for this E, the alpha at this E is going to be the sum. Actually, let's take this guy. The alpha for this E here is going to be the sum of these three alphas times by 2E. Whereas the alpha for this here is going to be just the sum of these two alphas times by 3B, because if I try to go two rows above, they are both the same symbol. So yes, Richard, what's the question? Why check if it's not the same as the symbol two rows above? That is exactly what we're checking, right? In the second row. So we're checking it because, again, that has to do with this fact, right? Look at the graph to the left. So you are allowed to go from horizontally within any row, right? So you're guaranteed that the row immediately to the left is a parent. You're allowed to transition down by one row from any row. So you're guaranteed that the row immediately above is also a parent. But then you're only allowed a skip if the row two rows above is not the same symbol as this one. And so that's why you have this check. You check if this symbol is the same as this guy, If it is not, then you sum this alpha. Otherwise, you don't. Did that answer your question, Richard? We are summing all three, right? When they're not the same. And so that's the sum of the three parents. And then you're multiplying it by the symbol probability. And that's going to give you the alpha for the node. So you can use this very simple rule to go down each row and compute the alphas for all the nodes. And eventually, when you're done, you'll have the alphas for all the nodes from the beginning to the end. And you can do the same thing going backwards with a slight difference, which is this. In the last row, you're only allowed, let's see, why is this so slow? So in the last row, you're only allowed to terminate in the, please, last two symbols. Something is happening. My laptop is doing crazy things. Bear with me. Okay. Okay. In the last row, you're only allowed to terminate in the last two symbols. So the beta hats are going to be 0 for all the rest of these guys, and they're going to be the actual symbol probabilities at these two nodes. Then you can go backwards, one column at a time. So here in the last column, only the last two rows have non-zero betas, the rest of them have 0. Then you go back one column at a time. Within each column, for any node, you would immediately be summing the betas for the, so consider this node, you would immediately be summing the betas for the node immediately to the right and immediately below, because you're guaranteed that both of these are children. Then you would check if that node has the same symbol as the node 2 rows below. And if the two nodes do not have different symbols, then you would sum that beta as well. And so going backwards, you'd be computing this for every node in the column. At each node, you'd be summing the betas for the two immediate children, the one immediately to the right and the one below it. And only if the two symbols on either side are different, will you also be summing the beta for the node 2 rows below. And so that's going to give you the sum of all the betas of all of the children. And then to that, you would multiply the node probability itself to get the beta hat for the node. Now, these are beta hats, meaning they include the node probabilities. You have to divide by the node probability to get rid of the node probability itself, because we know that the betas must not have the node probability included. Yes, Richard, was there another question?
Yes, Prof. Under what condition would the row or the element 2 rows below be the same?
Like in this case, right? Over here, look at beef. So this symbol sequence has 4 symbols, right?
Yes.
So these two are the same. Read, R-E-E-D, right? So the two E's are the same. You need a blank in between.
Okay.
To answer your question?
So, but I thought if there's a blank in between, you actually want to take that into consideration.
Meaning?
Or why are you ignoring the second symbol?
We're not ignoring any symbol, right?
Or I mean, not adding it to the calculation.
So we are saying, think of this. If you take any path from beginning to end and if you compress it, right? If you didn't have the blank over here, the two E's would compress to a single E, correct?
Yes.
So you don't want them to compress, which is why a blank is required. Whereas over here, in this case, regardless of whether I had a blank in the middle or not, the repetitions of B's followed by whatever optional blanks followed by E's is going to compress to a E.
Okay.
Right.
That makes it clearer.
Yeah, okay. That's all. The blank is invisible, right? And so that's the No, this is a hypothetical one, Laura. I came up with a really crappy example, that's all. This could have been read, right? And redoing this figure is very painful, so I've never redone it. At some point I must. But yeah. So anyway, that gives us the complete forward and backward computation. Posteriors and derivatives are computed exactly as before, but using the extended graph with blanks. And so the overall training procedure for sequence to sequence with blanks is going to be, I'm calling this sequence to sequence, we'll see why in the next class. You're given inputs and output sequences without alignment. You must train the models. First, you set up the network, typically a many-layered LSTM, but more recently, we also like to use transformers, which we will cover later. And then you initialize all parameters of the networks. You must include a blank symbol in the vocabulary. And then for each training instance, you would compute in the forward pass, you would compute the probabilities for all of the symbols. And then you would pull out all the necessary rows and compose this table from the probability table output by the network itself. And on this table, make sure to insert blanks on either side of every symbol, and then you compose this graph. And then on the graph, you perform the forward and backward computation to get the alphas and betas. Then we know how to compute the gammas. In any column, the gamma is going to be the product of the alphas and betas normalized. Yes, Richard, what was the question?
On the diagram for on the left, the YB, there seem to be 3 arrows. So I wanted to know if that was an error emanating
No,
from
over here, because B and E are not the same symbol, right?
Okay. Oh, okay. So it is related to that thing. Sorry.
Yeah.
Okay.
Whereas over here, E and E are the same symbol, so you don't have the diagonal arrow, right?
Thank you.
The blank is optional between B and E, but not optional between E and E, right? So
Thank you.
Chetan, what is the question? Why do we have only one row for blanks in the larger table? Because all of these blanks are identical. They're the same blank. It's like the one row for E's. The blank is just part of your vocabulary. So the network is going to be computing probabilities for all of these symbols and the blank as well. Did that answer your question, Chetan?
Would the probabilities not have to change after each one?
So no, consider this, right? This is the recurrent network. At each time, it's computing probabilities for all the symbols, right? So for example, it's only computing a single probability for E. But when we compose this graph, we made 2 copies of it for the 2 E's, right?
Yeah.
Same thing with the blank. The network itself is computing a single probability for a blank. But when we compose this graph, we just repeat that row many times.
So each of the columns here are one time instance.
Exactly. Right? Any other questions? And so once you compute the gammas, you can compute the derivatives. We saw how this is done earlier, right? The derivative with respect to the output probability for any symbol is going to be simply the sum of the gammas over all the rows which include that symbol divided by the probability of the symbol itself, the negative of this term. And once we have this derivative, which is the derivative of the loss with respect to the vector, this vector of probabilities, that can be back propagated through the network. Any questions? Yes, Vibha?
I had a question about the like the previous step, which was just the backward pass. So just wanted to know, computationally, do you actually need to make multiple copies of the row with the blank, or
You don't. So if you actually look at the slides, you can do this very efficiently just using pointers, right?
Mhm.
You don't actually explicitly compose this graph, but this is virtually what you're doing. How you actually implement it is up to you, right? There are many efficient ways of doing this without explicitly creating this table with a little bit of housekeeping. So take a look at the slides. There's some pseudocode for it.
Okay, thank you.
So, all right. And so the overall framework we saw is referred to as the connectionist temporal classification, or CTC, which applies to models that perform order aligned but time asynchronous inference, right? Now, there's one final problem, which we briefly alluded to two lectures ago on Monday, and we'll revisit it. And that has to do with inference. Now, when we didn't have a blank, if we just pick the most probable symbol at each time, we had an issue which said we couldn't make out whether there were repetitions or not. But then there's something more. When I'm performing inference, if I simply pick the most probable symbol at each time and then compress the sequence, is this finding the most likely time synchronous sequence, or is it finding the most likely compressed sequence? But here is the situation, right? So let's say I have an input of length 6. So here are 6 different time synchronous hypotheses. The first is RR blank 2 E's and D's with a probability of 0.7. Then it's RR blank blank ED with a probability of 0.68. You see how these numbers go, right? Now, if I pick the most likely symbol at each time, which one would I pick? What would my output be on this one? Anybody? It's going to be TED, right? Because that is the most likely one. But then if you look at the various other ways of aligning TED, the next highest one in my hypothetical example has a probability of 0.3. And then after that, it has a 0.29. Whereas if I look at red, there was an alignment which was pretty close to 0.71, but the second and third highest alignments also scored fairly highly. So which of these two would you think is the more reasonable thing to select in reality? Would it be TED or red? It's going to be red, right? It's more robust to jiggles in the alignment. So what we really want to do is this. We want to pick this guy, the symbol sequence whose total probability across all alignments is highest. Not merely the symbol sequence whose most likely alignment has the highest probability, but the symbol sequence whose total probability across all alignments is the largest. Now, the surprising thing is because of the way blanks work, if you simply pick the most likely one, you tend to get the correct thing most of the time. So here was a very nice example from Graves in their paper. And so, several of you asked this question, why do I introduce blanks where they aren't even required? It turns out that the blank ends up capturing steady state. So when I have something of this kind happening, here's what happened. I had steady state and then I had transition right here. Then I had steady state for 2 instances where, nothing really was happening. And then there was a transition right here. And so it turns out that blanks capture steady state. The blanks end up being the equivalent of nothing exciting happening here. And so if you look at the probability of all the symbols as a function of time, what you observe over here is, so this was for some word, and you can see that if you look at the dotted line, shows you the blank probability of the blanks. So the upper one, I think, is, if you don't actually, I don't know what the upper one is, the lower one is more interesting. And you can see the lower one, the dotted line, in most of the steady states, the blank ends up capturing most of the probability. And the other symbols simply peak up right where the transition is happening. And so if you simply pick the most likely symbol at each time, you actually end up capturing simply because you tend to get just one or two highly likely alignments, and the rest of them, you get very little variation in these other places because the blank sub consumes most of the probability. And so if you simply pick the most likely alignment, that's the greedy decode, you'd end up getting the right output most of the time. So the blank does a very nice job of capturing steady state and makes the greedy decoder functional. But then in reality, what we really want is, going back to our previous example, we want to find the symbol sequence which has the highest probability across all alignments, right? And so what is the total probability of a symbol sequence across all alignments? That is the alpha right here, right? So if I wanted to compute the probability of B phi for an input, I would have to compute this total probability across all alignments, which means I'd have to compose this graph, run the forward algorithm, and compute the alpha out here. And that alpha is going to be the total probability across all alignments. And I'm going to have to pick the symbol sequence for which this alpha was highest. So the actual decode I would be performing was this. I'd be inspecting every single possible symbol sequence. And then I'd also be considering blanks to be sure, right? And then I would compute the alpha at the bottom right over here and pick the symbol sequence for which that alpha term was highest. Did that make sense? Did that make sense, folks? Yes or no? Vibha will get to that. But did the general idea of how we must be performing inference make sense? The rest of you? Okay. What about the rest of you? Did that make sense? Richard, did it make sense? Richard?
Yeah,
Okay, so Kim, what do you mean by not clear how it solves the problem? Can you
the
explain?
problem of selecting the greedy approach. I thought this was supposed to solve that greedy approach.
So
But I
here,
don't see.
so here's what is happening. Do you agree that this is the total probability across all alignments?
Yes.
Okay. And so do you agree that what we really want to do is to pick the symbol sequence that has the highest total probability?
Yes, yes.
And so does this equation make sense?
Because I was thinking this would also do the same operation as the greedy approach.
How is it?
Yeah, so I was wondering what the difference was,
So,
or how would it
okay.
solve?
Is this
Yeah.
alpha simply the probability of the most likely sequence through the graph?
Yes,
Is it?
I think so. Because I'm
Wait,
assuming
how did we
you
compute
derived
alpha?
the alpha through
Yeah.
the greedy
No,
as
how did we
selecting the
compute the
highest
alpha?
problem.
How did we compute the alpha?
By taking the probability of the, should I say, if you take the previous part, you take the two or the three
Yes, so
previous rows. Yeah.
so the alpha is summing over all paths, right?
Okay.
Is that greedy?
Okay. No. Okay, I understood.
Not greedy, correct? Yes. So this is what we'd want to do. So what would the problem be with doing this? Trying to do this. Anyone?
Is
What
it
would-
like you'd have to actually find out every single possible every single possible sequence and then find the alignments
Yeah.
and then okay.
Yep. And that's going to be incredibly expensive, right? So this is not a poll, but that can you guys vote on this? The actual objective of decoding is to identify the compressed sequence that has the highest probability given the input, true or false. Rest of you, I'd like to see your true or false. Okay. And this is the same as finding the compressed sequence with the highest forward probability for aligning the final symbol to the final time instant, true or false. Also true, correct? Both are true. So this is the real issue, but then explicit computation is going to require evaluating an exponential number of symbol sequences. So here's what I'm going to do instead. To simplify the problem, we come up with an engineering solution. I'm going to organize all possible symbol sequences in the form of something that looks like a tree. First, the very first, remember that blanks are invisible when you compress it, right? So the very first symbol can be either a blank. I'm assuming that in this, for my trivial example, I have only two symbols in my vocabulary, S1 and S2, right? Like maybe A and B, okay? So my very first symbol could be a blank, or it could be the S1, or it could be S2. So this is the initial portion of the, this represents all possible symbol sequences of just length 1. It could just be S1, it could just be S2, or it could be blank S1 or blank S2. When compressed, this whole collection is going to become either S1 or S2. Did this make sense, this visualization? Okay. So rest of you, did this visualization make sense? Okay. Now look, S1 could be followed by an S2, right? But then S1, for S1 to be followed by an S1, there must be an intermediate blank. Again, the blank is invisible, but it must be there, right? You can't have S1, S1 without the blank because it would compress to just S1. But then S1, a blank can also happen between S1 and S2. So the upper portion of the graph represents all symbol sequences of length 2, which begin with S1. Did that make sense? Right? And Richard, this makes sense?
Well, I'm wondering why there's a blank, or there's a path from through the blank to S2.
Because S1 blank S2 is also going to compress to S1 S2, right? Because the blank is invisible.
Oh, I thought we had already compressed.
No, I'm speaking of the final compressed sequence. So I'm saying it's invisible, but it's there, correct?
Okay.
For you to see S1 S2, you can either have S1 S2 or S1 blank S2, correct?
Yeah. Okay.
That makes sense? Remember, think of the blank as an invisible symbol. It's very much there. It's just not visible, right? Okay. So we have the S1, but then for the path from the S1 to S1, it must go through the blank. Otherwise, you can't have two S1s in a sequence, right, Chetan? So this is.
But in the previous tables, you had the horizontal arrow going.
Okay, so this, okay, over here, this is the aligned. So these are alignments. So you can have repetitions. BBB is going to be just a single B, right?
Yeah.
Here I'm speaking of the actual final compressed sequence, which will include the invisible symbols. Nothing repeats.
Okay.
Right? And similarly, all sequences of length 2, which begin with S2, are shown by the lower portion of this picture. So did that make sense, folks? This one here? Okay. And so here is the entire graph for all symbol sequences of length 3. This figure makes sense. Over here. Okay, and so this is what I'm calling a semi-tree because you have these things, these direct connections and the connections from a blank. It's not an exact tree, but it kind of is like a tree, right? And so here's what I will do. I take this graph and lay it out on the vertical edge over here. This figure to the left is exactly the same as the figure over here. I just sort of arranged it vertically, right? And corresponding to this, I can now make this graph. So the horizontal edges represent repetitions of a symbol, which will compress to a single instance of the symbol. And then all the other diagonal edges represent all of these possible transitions. This figure to the right makes sense?
Oh, one last thing.
Yeah.
I realized the blank at the bottom has a horizontal symbol, but it has no direct connection to the blank at the top
It
or the
doesn't.
next blank. Yeah, so then with that logic,
No, because if a blank connects to a blank, then everything between the two blanks will will disappear, right? You can have a
yeah,
path which doesn't include those.
yeah.
So
So then with that, what would the horizontal arrow for the blank mean?
So the blank is just, look at this guy. If I just had blank S1, if I aligned it to an input, it could just be blank, 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 S1, 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 right?
Yes.
So that's what this blank means.
Yeah.
These
So
are
in the
just
graph, I was expecting the horizontal for the blank to not be present. That's what
blanks
is
can repeat,
confusing.
can they not? I mean, go back here. Blanks can repeat.
Okay. Okay, so is it this a case of it being invisible, but it's actually present?
Yes.
Okay.
So you have to think of the blank as invisible. That's it, right? It's present. So, okay. The dashed lines are just the rest of the graph going up. This tree is going to be infinitely deep. That answer is Sushan?
Yeah. Okay.
Okay. There's only so much I can show on my slide. But again, this has not solved the problem because I just constructed something which is infinitely large. The figure to the left is my semi-tree drawn in a vertical line. The graph is just the tree unrolled over time, meaning I've just added horizontal edges. So for a vocabulary of V symbols, every node connects out to V plus 1 nodes at the next time, right? So with the V nodes, if you also include the blank as a vocabulary symbol. Now observe this over here. If I, that's my, look at this guy over here. This any node on this row represents this S1, correct? It's just repetitions. So if I'm anywhere on this row, it basically means that the only two symbols I've output are repetitions of blank and repetitions of S1. That makes sense? Yeah. So being present on this row means that I have generated S1, right? Similarly, every node on this row represents blank, represents S2. It's either a blank S2 or just S2. But if I'm anywhere on this row, it means that I'm representing a symbol sequence consisting of just one visible S2, right? Make sense? Okay. Similarly, if I'm on this row over here represents this node. If I'm anywhere on this node, it basically represents a symbol sequence which consists of a visible S1 and a visible S2. That's it. So this entire row represents the sequence S1, S2. Make sense? What about the rest of you? That makes sense. Okay, so here's what, so we're going to take advantage of that, right? If I stop at any time, each row represents a different symbol sequence where I've explicitly also shown the invisible blanks. This one is simply the symbol blank. This row is just S1. This row is just S2. This row is just S1 blank. This row is just, it's actually S1 blank S1. So I should have actually written S1 blank S1 over here, but it collapses to S1. But here's the thing. This row represents both S1 blank S1, and it also represents, yeah, that's about it, right? Now this row represents something interesting. It represents S1, S2, it represents all ways of producing S1, S2. So this can be, it includes both S1, S2. It also includes S1 blank S2. So this row represents just S1, S2. This row represents S2 blank. This row represents S2, S1. And it includes both S2 followed by S2 followed by S1. It also represents S2 followed by blank followed by S1. So this row represents this node, and this node represents S2, S1. Again, to understand why, you have to look at this graph, right? This node over here represents S2, S1, including all ways of writing out S2, S1, including the invisible blank. That makes sense? This just represents S2, S1, right? Then, guys, do you see how this, yeah, okay. So that means correspondingly this node here, yes, exactly. So this node, this row represents every possible way of composing S2, S1, right? And so if I compute the alpha at this node, that's going to give me the alpha for S2, S1. The alpha here is going to give me the alpha for S2, S2. And so if I could just compute the alphas for all the nodes in the column over here, then, and I pick the most likely alpha, I'm naturally going to pick the symbol sequence which was most probable. That's it. And so the problem basically reduces to, basically those are the alphas, right? So the problem just basically reduces to computing the forward algorithm on this graph. And then when you run out of inputs, you pick the symbol sequence with the largest alpha. Make sense? Okay, and so, of course, you have computational issues because this graph blows up exponentially. So here's what we do. At the first time, at time 0, we have to compute the alphas at these 3 places. Then at the next time, you compute all of these alphas that these guys lead from. But then instead of retaining everything, because we are likely to run out of space and compute, we will retain only the k best. In this example, I've chosen k to be 4. And you delete everything else. So all that remains are those 4 that have not been crossed out. And then at the next time instant, you're going to expand only the 4 that survived. That the 4 that survived can still give you a fairly large number of nodes activated at the next column. But then again, from those nodes, you only retain the best 4. And then you're going to expand those 4 again to the next instant, and then retain the best 4. So what happens is that each node can expand out. If you have a vocabulary of V, each node can expand out to V nodes at the next time instant. If I'm retaining 4 nodes over here, I'm going to have at most 4 times V nodes evaluated over here, of which I only retain the top 4. And I keep doing this. So the computation never blows up.
Question?
Yeah.
You said top 4, but I see 5 selected in the second.
So have you seen 5? No, 1, 2, 3, 4. The rest are crossed out. They're killed.
Oh, okay. I'm rather looking at the cross ones.
No, I've deleted those, killed, right?
Okay.
So, no, this is not, so this is going to be suboptimal, but it's computationally, it's what we can do. This is an approximation, you're right here. And so this is what we will do. And then when you're done, you're going to have performed this computation. And in this case, I've chosen what? At the final time instant, you can just consider all of them, right? There's no need to prove. And so you're going to have all of these alphas over here. And then if you want to compute the score for S1, you actually have to sum the scores for S1 blank and S1 because the final blank is invisible, right? And so you just compute the scores for, you got the alphas for all the symbol sequences where you might have to add some terms because S1 and S1 blank are the same thing. The blank is invisible. So you'd add these two alphas to get the score for S1. And then pick the sequence for which the alpha was largest. And that's going to be your best hypothesis. That's going to be your decode. Did this process make sense? Right. This is what we call our beam search algorithm. There's some very ugly pseudocode on the slides, but we have a much more compact pseudocode. I'll probably replace the ugly pseudocode on the slides with a more compact one from Chen and post these slides again. But that's it. And so this beam search is something that you guys are going to be implementing in your homework. Yes, Chetan. So typically we pick a K that we can deal with computationally, but we often find that going over, 8 or 7 or 8 doesn't really buy us anything. By the time you're down to 8, you get most of the bang for the buck. Good. And so that's the story so far. These are sequence-to-sequence networks, which take in a sequence of inputs and produce another sequence of outputs, where the output sequence may not be the same length as the input. And they can be trained either by iteratively aligning the target output to the input and using time synchronous training, or optimizing the expected loss over all possible alignments. Distinct repetitions of symbols can be disambiguated from genuine repetitions by using the blanks. And decoding can be performed using best part decoding. This should not be called Viterbi decoding, it's greedy decoding, or optimal CTC-based decoding based on the application of the forward algorithm to a tree-structured representation of all possible output strings. So that's it. That's the end of this lecture. Do we have any questions? Any questions? All right, if there are no questions, thank you very much for your time and patience. I'll stop the recording.